Good day, everyone. So, today we shall be looking at a topic simple harmonic motion. When you talk about the simple harmonic motion, which is sometimes shortened as SHM, you are talking about motion that repeats itself. Motion that repeats itself. The word harmonic actually means repetition. Let's take example of this. Now, if you look at this first diagram here is a loaded spiral spring. You can see it moving up and down. This up and down is what we refer to as to and fro. It's repeating its movement from up to down, up to down. That is a simple harmonic motion. Some other time we call it periodic motion. Another example is a moving pendulum. You can see it, a swinging pendulum moving to and fro from left to the right. Okay, another one is a loaded test tube in a liquid. You could see that moving up and down, up and down, up and down. So that repetition of movement from one direction to the other is known as simple harmonic motion. So we say it is a periodic motion of a body or a particle along a straight line so that the acceleration of the body is directed towards a fixed point. Each of them at a fixed point. Okay, this is a fixed point for this spiral spring. This is a fixed point for this pendulum bulb, and the fixed point of this test tube is in the liquid. All right, so those are the examples that we can say, we can state for simple harmonic motion. Now, there are some terminologies we have to also be familiar with, and the first one is the linear velocity of an object undergoing simple harmonic motion, and also the angular velocity of the object. Now, when we talk about linear velocity, we are talking about the object moving along a straight line, okay? But when we talk about the angular velocity, we are saying that the object is moving in a circular form. Look at this object here. This object is moving in a circular manner. You can see that it's moving in a circular manner, and as it's moving, it gets to the starting point again. This place is the starting point and moves again. All right. Now, in this movement, it has been observed that there is a particular distance from the equilibrium position, that is the starting point from this center here, towards this line X. That line X is the displacement of the object from the starting point, which is called the equilibrium position. And then there is also referred to as amplitude, that the maximum displacement of the object between this point and this point is called the amplitude, and is represented with letter A. And then the angular displacement is this theta here, this angle here. Okay, so we have the displacement from the center, which is the X, the amplitude, which is the maximum displacement, and the angular displacement, which is the theta. All right, now we are going to derive some formulas with all these letters. Okay, now going back to the screen, we have this angular velocity to be theta over t, where the theta is the word angular displacement, and it is taken to be 2 pi n. The n represents the number of circles the object has moved, the number of circles that it has gone round. Okay, so the formula for angular velocity is theta over t. So we say by definition it's defined as the angle turned through divided by the elapsed time. And if we cross multiply this, we have the theta to be equal to angular velocity times t. On the other hand, the linear velocity is defined as the time rate of displacement. We've said it before. Then that was v, which is the linear velocity, is equal to x over t. And if you cross multiply that, we also have x to be what? Vt. Again, we have v to be angular velocity times radius, the radius of the circle. All right. So sometimes we refer to this as radius, this amplitude. Sometimes it is referred to as what? As radius. All right. So coming back to this, we have V to be equal to W omega R. That omega R is not referred to as W. It's not actually W. It's a Greek symbol that we call omega. So WR or WA, because sometimes R is taken to be amplitude. So V also has the formula of omega R or omega capital A. Another formula for linear velocity is omega square root of amplitude square minus x square. Of course, where the x is the displacement from the equilibrium position. Now, for us to obtain our maximum velocity, that will be at the point where x is equal to 0. When x equal to 0 here, then our v will now become omega a. Okay, so the maximum velocity is obtained at when x equals 0, where vm is the maximum velocity, and that is equal to omega a. Meanwhile, the minimum velocity is occur when x equals a. Of course, when x equals a here, everything here will become what? 0. All right. Now, another formula again that we need to know that's relating linear velocity, angular velocity, and acceleration is this. Acceleration equals to minus omega square a, or acceleration equals to minus omega square r. Remember I said that a can be substituted for what? For r. We use them interchangeably. So radius or amplitude in simple harmonic motion are taken to be what? To be the same some cases. Again, acceleration can be equal to what? V square over r. So all these formulas are very key in solving problem in simple harmonic motion. Okay, now the minus sign here shows that the acceleration of the object is always acting toward the center, toward the fixed point from where the object is moving from. That's what the negative sign represents, that the acceleration is acting toward the center, meanwhile the amplitude is acting away from the center. Okay, so having said that, let's consider energy that is stored in swinging pendulum. Look at this swinging pendulum. As it's moving from left to right, to and fro, it is storing two types of energy, and that is potential energy and kinetic energy. The potential energy stored by swinging pendulum by formula is mass times acceleration to gravity times height, where the mass is the mass of the pendulum bob, the m is the mass of the pendulum bob, the g of course is a constant which is 9.8 or 10, and the h is the height of the string that is holding the pendulum bob. Then the kinetic energy formula is half mv squared, where the m still remains the mass of the bulb and the v is the velocity of the swinging pendulum bob. Now, it has been verified from the conservation of energy, from the law of conservation, that the total energy in a swinging pendulum is constant. In other words, EP plus EK is always what? The same, no matter how you speed up this swinging pendulum bob. So this diagram here is showing us a typical state of the energy when the swinging pendulum bob is at the extreme left here. Then the potential energy is at the maximum, while the kinetic energy is at its minimum. So potential energy is at its maximum because the swinging pendulum attains a particular height from here down to this place. So that shows that the potential energy is at its maximum. But at this point here, this particular point here, at equilibrium position, the potential energy is at its minimum, while the kinetic energy is at its maximum. Then at the other end, okay, the potential energy is at the maximum and the kinetic energy is at the what? At the minimum. So at both extreme ends, they have the same result. Okay, so that is the formula that we have for a swinging pendulum in simple harmonic motion. Now, aside from swinging pendulum, we also have a loaded spiral spring, energy stored in a loaded spiral spring. The total energy stored in a loaded spiral spring is half Ka square, where the K is known as the force constant. Of course, the force is the force that is making the spiral spring to move to and fro. And then the A remains the amplitude. The amplitude is just the displacement cover. You can see this object, its amplitude is the distance covered from up down. Okay, from this point downward, the displacement is not at the what? At the amplitude. Again, the law of conservation of energy still holds here. The total energy still remain what? Constant. In other words, potential energy plus kinetic energy remain constant. And by formula for energy in a loaded spiral spring, the potential energy is half Ky square, where the K still remain the force constant and the Y is the displacement. In this case, now we are using Y in place of A. And the kinetic energy still remain half mv square. Okay? So, in a loaded spiral spring, potential energy is half Ky square. Meanwhile, in swinging pendulum, it is mgh. Please take note of that. Now, the total energy, we have said it here. If we bring all of this value here, we'll be having half Ka square equals to half mv square plus half Ky square. So aside that, from the laboratory, it has been verified that capital T, which is called the period, is equal to 2 pi square root m over k, where the m still remains the mass that is connected to the spiral spring, and the k remains the force constant. Again, period, which is capital T, is equal to what? Inverse of frequency, 1 over f. Again, angular velocity, which we sometimes refer to as angular frequency, is equal to what? Square root of k over m. And lastly, angular velocity equals 2 pi f. Okay, so that's it. Now, having seen all of this, we will then have to see an example on all of these formula we are talking about. Now, look at this question. It says a body of mass 20 gram is suspended from the end of a spiral spring whose force constant is 0.4 Newton per meter. The body is set into a simple harmonic motion with amplitude 0.2 meters. Okay, calculate the period of the motion, B, the frequency of the motion, C, the angular speed, D, the total energy, E, the maximum velocity of the motion, and F, the maximum acceleration. Alright, in solving this problem, we will need to consider our mass first. All our parameters should be written out. Mass of the object is 20 gram. But when we are solving problems, we always convert our quantity to the what? To the SI unit. 20 gram has to be converted to what? To kilogram. So mass, which is our 20 gram, to kilogram will be what? 0.02 kilogram by dividing with 1000. Again, we are told that it has a force constant, that is K. So K here is 0.4 Newton per meter. And then amplitude, which is capital A, is 0.2 meter. So the first question says we should calculate the period of the motion. So period is capital T. And by formula, capital T is equal to 2 pi square root of m over k. Now that will be equal to 2 pi. Substituting the value of m, which is what? 0.02. We have 0.02 here. All over our k, which is 0.4. Then if you punch the calculator, you'll be having a final answer to be 1.41 seconds. Your pi, of course, is 22 over 7. So that being simplified will give us 1.41 seconds. So our period is measured in seconds. Then B said we should calculate the frequency of the motion. The frequency of the motion. So the frequency of the motion by formula is 1 over period. And that will be 1 over 1.41. That is giving us 0.71 hours. Frequency is measured in hours. The third question says we calculate the angular speed. So by formula, angular speed is 2 pi f. So we now have 2 pi times our f have been obtained in B question, which is 0.71, and we have it to be 4.46 radian per second. Angular speed is measured in radian per second. The next question says we should calculate the total energy. Okay, that's D. Now the total energy by formula is half Ka squared. Of course, our K still remains the first constant, which is 0.4. We substitute it here, and our A, the amplitude, which is 0.2. That's 0.2 square. And if you simplify, you have 0.008 joule. Energy is measured in joules. The next question says we calculate the maximum velocity. Maximum velocity is calculated with this formula omega A, and our omega, which is the angular velocity, is 4.46. So we bring it here, it's 4.46 times our amplitude, which is 0.2, and then we have it to be 0.82 meter per second. And the last question is we should calculate the maximum acceleration. So the maximum acceleration by formula is omega square A. So that will be 4.46 square times 0.2, and that will give us 3.98 meter per second. Okay, so this is how to calculate period, frequency, angular speed, whatever question, maximum velocity in simple harmonic motion. So we are going to be drawing the curtain here for today. In our next class, we are going to learn more on this. Thank you for listening.